Embedded Controller Lab. Today we will discuss an experiment. Display hex digits 0 to F on 7 segment LED interface with the appropriate delay in between. So before we begin with the program, the components required. So we require a common anode mode, 7 segment module, and this is its schematic diagram. So since it is common anode, the LED's positive terminal is made common and it is connected to a positive voltage, and the other end is left floating. And if you want to make or turn this LED on, you need to connect this end to the ground potential. So if uh, you want to blink this three LEDs, so make this ground, connect this to ground, G to ground and F to ground. So this three LEDs will glow and the remaining will be in floating mode and it will not turn on. So the common logic over here is to turn on. Probably if you want to display a digit 0, then this is actually the segment which we want it to be off, and the remaining digits on or remaining segment should be on. So we go like this in this direction. We know this terminology: A B C D E F G, and this is HDP connection. So we expect A, B, C, D, E, F to glow and G should be off. So this is your table diagram. X value what we are supposed to load to get 0 displayed. So G should be pulled high. G should be pulled high, and also H should be made high because this should not glow. That's the indication, and the remaining should glow. So whichever segment you want it to glow, make it low, others you make it high. So here we expect G and H or DP to be no, it should not glow, hence it is made one, and the remaining segment should glow. So 6 segments we expect it to glow, that is A B C D E F. Okay, so in that case you will be getting the value 0 displayed on this 7 segment module. So the remaining digits are also displayed in the same manner, so its equivalent X code would be F9A4, so on. So hope this concept is clear. The next we will talk about a register which we will be using here. The reason why we are using that register we will discuss. Suppose if you want to interface a microcontroller with a 7 segment display, so definitely 8 terminals we require, 8 pins of your particular microcontroller we will be making use. So in that case, the hardware complexity of the design will go on. It will be more complexity of designing is more. Also the total number of pins which you are going to utilize will also be more. So in that case, it's also possible to make one pin use. You can use only one pin, and the remaining pins you can use it for control signal application. And you can instead using one pin of the microcontroller, also it's possible for you to interface it with LCD 7 segment module, not LCD 7 segment module, and you can display the digits, but you require a shift register. So this register comes handy here in case if you want to transfer 8 bits simultaneously to your 7 segment. So from microcontroller to the DS line, let me talk about the pins. So this shift register, you call it as 8-bit serial input, and it can provide you serial output or parallel output. So in this mode, serial inputs are given to the shift register, and the parallel outputs are taken out from this shift register and it is given to the 7 segment. So altogether 8 parallel lines you can take out, and those are addressed as Q0, 15th pin, Q1, Q2, Q3, Q4, Q5, and Q6 and Q7. So altogether 8. And there is one more pin, Q7. Suppose if you want to transfer data from one shift register to another shift register, then you can always use this Q7 terminal, which means if say that the data available at Q7, if I want it to be transferred onto the Q0 line of the second shift register, then you can always use Q7, you can connect it to DS line of the second shift register. So there is a communication established from one shift register to another shift register, so you can transfer the data from one register to another register. So that's required here, because in this application we will be using 7 segment display modules. 7 segment display modules are used, and in all the 7 segment display modules we are going to get a digits displayed. So it's something like 0 to F will be printed or displayed on all the 7 segment modules. So the logic to enable this module, output enable pin should be triggered low, and master resets pin should be triggered high. Master reset, if it's triggered low, then basically what happens is the content present, any information temporarily if it's stored here, will be vanished off. It is to reset your master. So this is having a memory 16 information, this is having 16 information. We will look at in detail what exactly this shift register has, and how exactly it is going to transfer a data which has been given to the microcontroller, and how that microcontroller data which is fed here, how it is going to go out from this unit to the 7 segment module. Okay, and the pin connection, which is important here, we will be using 3 pins of your microcontroller: P21, P20, and P22. P21 pin, port 2, 1th pin is connected to data select, and P20 is connected to SHCP, shift CP. This is for serial shift, and stored. This is for storing purpose, storing, or else you call it as latch clock. Remember, P22 is latch clock, and P20 is shift clock. The shift clock has to be provided always when you're transferring one bit from microcontroller unit to your shift register, then you have to supply this. And this latch clock would be provided once you have all this 8 bits available in your shift register to transfer those 8 bits to the 7 segment module at one stretch. Then you have to provide this clock, which you call it as latch clock. Okay, and the connection from 7 segment module between 7 segment module and your shift register goes like this: Q0 to Q6 connected to A line to G line, and H line is also available, so that can also be connected from Q7, no problem. So Q7 can be connected to H, no issues. um, Hope this connection is clear. Now let's look at the working of the shift register, how it is going to send data, and how it is going to grab a data. Literally this shift register is having altogether 16 D flip-flops. Okay, so this are the D flip-flops. On the lower end I have D flip-flops. This is to collect the data serially, and once the latch clock is enabled, the data which is available on this lower side of this, or lower D flip-flops, 8 D flip-flops, they get transferred to the upper 8 D flip-flops when the latch clock is made on. So how do you receive a data? To receive a data, as we know, P21 will be connected to DS. So one bit at a time can be fed here. Assume that you have a data 101. 101 data is there in the buffer, and we want that data to be pulled onto the shift register. So first what we do is we make the clock bit is initially set to 0, implies you don't have information. So if you want to collect the information, one bit, if it needs to be transferred to this end, then apply the clock. When the clock is applied, and if there is any information present in the DS line, say that now you have 1 here, and if we want that 1 to be outputted over here in Q, if we want that 1 to be available, then the shift clock, or this clock, this is for serial clock should be made 1. So when you make this one, any data which is available over here, you're gonna get it over here. Okay, so at this D flip-flop end, you are going to receive 1. Now let's assume that the next bit is 0. So you have to shift the data using some methodology, using some program. Then you get 0, and that 0 will be over here now. Now again, to get that data onto this end, again you provide 1. So previously you had 1 here. Okay, so when the clock pulse is given, now when during the rising edge of the clock, this 1 gets transferred here, and the 1 which you are having at the data strobe line goes to this end. So here you are having 0, so 1 gets received here, so you get 1 here and you get 0 here. Now the next bit is 1 and then another 1, so shift the data again using program, and that data, to receive that data again, make this clock high, make this clock high. So once the data goes on to the shift register, you have to pull that clock pulse to low, then only during the next iteration when you make high, then the data can be transferred properly. Okay, so this way it goes. Now assume that after application of 8 shift serial shift clock pulses, you have all the data. Assume now you have information something like C0, C0, first 1100, then 0000. So which means here you just assume 1 would be here. After application of 8 clock pulses, that 1 goes here. Okay, then assume since it is C0 value, after 8 clock pulses you will be getting here 1 1 0 0 0 0 0 0. So you read it as C0. Now all those information would be transferred here. If I want those to be made available, then what you have to do is this latch clock should be made 1. So when you make this 1, whatever the data you have over this line will be transferred, because this is the structure what you are having. So you have q goes to the data and you apply the clock. So on to this q, you get 0, and this is actually your tri-state buffer. So this buffer data what you have here will also be made available here, and this should be made 0. So OE enable, if it's set to 0, then you get 1. So if this is 1, then only the data gets received. So don't make output enable pin high. Output enable pin, if it's made high, then you are not going to receive any data onto this line. So hope to some extent you are convinced. Now let's look at the program with respect to that. We will talk about the whole structure. Before that, the interfacing diagram we will talk about, the interfacing between the microcontroller shift register and the 7-segment module. So this is the structure. So if this pictorial diagram is not clear, we will provide you this data sheet. So what you have here is FRC cable connection. So this is your 1 2 3. Concentrate on this pins. 1 implies it is P20, 2 is P21, and 3 is P22. Okay, so only 3 pins we are making use, and then you have the ground and VCC connection. Okay, this is G VCC, and this is ground connection, which is 10th line. Okay, so you can just observe, which is the 10th is MR. So MR is made, it has to be made high, it has to be made high, so that's correct. And one more is 8, I guess, if I'm not wrong. So yeah, ninth pin is given to SCL. Okay, that's is it ninth? Yeah, ninth pin is given to serial clock. That's for it's a clock. We will talk about these 2 lines. What basically they are into, and these 3 are for data signal. This is 13. This is 10, and this is 13. Ninth, sorry, this is FRC9. FRC9, you can assume it as VCC and ground. Don't worry about this. This belongs to FRC9. Don't get confused with the pin numbers of your shift registers. Okay, so one is ground, one has to be given to ground, and one more has to be given to VCC terminal. Okay, so that's 9 is given to 10, and this 10 is given to 13. So concentrate on 10 and 15, I guess. 10 and 15, 10 and 13, 10 and 13. So this is OE. So this is high and low. That's correct. 10 and 13, 1 and 0 you are supposed to provide. So that's what the connection is. This is high, this is low. That's for master reset and output enable pin. Okay. Now the connection is as addressed P20, P21 and P22. They are connected to data signal, clock, serial clock, and latch clock, and it is addressed here. The pins on the side of this one. So DS, this is connected to P20, DS P20, sorry, P21, and P20 is connected to shift 11, and this STCP, which is for latching, P22 is connected, and that connection you can observe here, 14, 11, and this is 3 is connected to 12. Okay, 12, 12 is yeah, latch, 12 is latch. So we will make use of 12, 11 and 14, 12, 11 and 14. So in this, if I'm not wrong, you can figure out 12, 11 and 14, and this is you know for selecting the output enable line and master select master reset line. And the connection between a shift register. So as addressed, if you want to transfer a data from one shift register to another shift register, there is the pin number 9. Pin number 9 is connected to DS of the second shift register. So one bit at a time from this register gets transferred to this unit, and similarly you have to follow that for the remaining shift register, so that all information from the segments 1 to 6 all will be displayed on those 7 segment modules. Coming back to the program, now this header file, we know what this header file is, and forget about this isn't required. We are not using convert display, so we will be using method display 6 digit. This is your main program, which in turn calls the method display, and we will create initialized array. We create a array, and in this array 16 digits code, 7 segment code are addressed, and this is for common anode. So we had observed C0 was for 0, F9 was meant for displaying 1. So this is in the order 0 to F. So 0 to F will be printed, and since the objective of this program is to display 0 to 9, 0 to F hex digits on the 7 segment module with the proper delay. So we will be using a delay method also. After displaying 0, then after a while 1 has to be displayed on the same 7 segment module. Okay, and we use one global variable count, and this count is used for comparing whether you have reached the maximum hex digit, that is F. If you have reached F, then you have to count, then the count should start from 0, and for that comparison we will be using this count, and literally this count has to be compared with the maximum value, which is 16. 16 cannot be achieved. If it is 16, then you have to change the value of count to 0, so that you get the message displayed. After F, again 0 will be displayed. 0 to F it displays, then finally from F again it goes back to 0, and the process repeats. Okay, the program, this is your program, and you are using port 2. Since you're using port 2, first 3 pins, which is addressed as P20, P21 and P22, the directional flags should be set to 7. 7 implies P20, P21 and P22 will be working as a output port. Is this hope is clear? Okay, and this is a small piece of code which you will be running, and what this does, we will talk about in a while. So first you have after configuring your pins, then the while function, while true, always run this program. So it calls display 6 digit count. We will talk about this later. And after it displays a digit on the 7 segment module, the count will be incremented, so that on doing this you are supposed to go back to this location, and you have to display 1 on it, and this process should be repeated. And if you find the value of count to be greater than 15, happens to be when you go to F hex value is 15, then you get 10 hex value. When that is the case, that's 16, then count should be set to 0. So on doing that again, it will point to 0. Okay, that's what we do. So this is our main program, and now let's look at this main method, display 6 digit. Let's concentrate on this. So this method is used for displaying a digit on the LCD 7 segment module, and here it takes argument display. So here, what is that argument? That argument is count, and first that count is set to 0 here. The count value is 0, which means you're calling display 6 digit of 0. Okay, so here display value is 0. Now you unsigned integer 6. The reason why you are using this iterator, x is equal to 0, x less than 6, it has to be repeated, which means 0 will be displayed on the 7 segment, first 7 segment, second, third, as well as fourth, fifth, and sixth. So all 7 segment module, 0 will glow. For that, we will be using this logic. So 6 times repeat this process. What is the process? It is to display 6, display 0. Now you are having a value of this as 0. Is it okay? Because count value is 0. That's the value which you're having. Now what you do is, you go to this method. Now you call again the method display. Now this display method, you define the logic. Notice shifting the data serially, everything is defined in this display logic. Now how this calls? So since this disp value is 0, when x is equal to 0, once this method is called, so first display of disp of 0 you have. Okay, now the display takes what? So display of what? Disp of 0. Disp of 0 is nothing but C0, right? So you're calling in turn display of C0. So one argument it takes, and that's your first number, right? So C0 is actually the number which is taken using display method. So you have display of C0. Now let's look what display of C0 does. So here it returns integer. It is going to return integer, and this display method does what? So it has value C0 now. Okay, it has value C0, and it is you know character m you have defined. So this m is required for iteration, because in your data, C0 data, you have 8 bits. Okay, 8 bits. And the buffer is also defined. You can define it as character, so it will be better. And what you do is, first you store this value, which is C0 value, will be stored in buffer. So buffer 2 has a value C0. Now what you are doing here is to you will check the MSB bit. You'll check the MSB bit, and if the MSB bit is 1, okay, if the MSB bit is 1, then you send signal, high signal. You send high signal on the line P21, because P21 is connected to data strobe, which means on this line you'll be receiving the data. So if you find, if this condition goes high, if this is true, then set bit to make it 1. If this goes low, if it is false, if you are not getting any result here, then bit 2 of port 2, that is P21 bit, P20, not P20, P21 bit, make it 0, send 0. So this sends 1 if you receive 1, and it sends 0 if you receive 0 in the buffer. After that, you use FIO set. So what is this FIO set? FIO set or equal to previous content of FIO set will be odd, and you're going to send 1 here, which means it is 1 itself. So it's no matter what the data is, it is made 1. That's to apply the clock. Previously the bit is reset, this bit is reset, okay, because GPIO you haven't used it. So that set is 1, which is 1, which is P20. P20 is meant for providing the serial clock. Now serial clock, initially it was 0, now you make it 1. Now the data goes to the shift register of your this module, shift register module. Then we shift it. Now C0 you have, once you use this, buffer is equal to buffer shifted by 1 bit. So what it does, so 1 bit you shift towards left, Okay, so 1100 becomes, I mean C0 is 1100 followed with 40, it becomes 80. Is it correct? So because 1 goes to the carry, that's 0, and not the MSB bit, the bit next to MSB goes to the MSB position, so you have indeed 8. Okay, so what basically it does, let's talk. So if buffer, what is the value of buffer? Buffer value is C0. C0 you make AND it with 80. When you perform C0 ANDed with 80, bitwise ANDing you do. So if that is the case, you get the result as 80 itself. You get the result 80. Is, it's think as if it's true, which means you have some information. It is not 0, which means this condition will be executed, which means you're sending 1 is sent. Okay, then what we do is we apply the clock and we shift the data. Now C0 becomes 80. Okay, then we make it low. The clock is set pulled low because again during the rising edge the effect takes place. That's why the clock is made low, done with the help of FIOCLR. So what is this FIOCLR? FIOCLR command ensures that the bit 1, that is P20, remains low always, low always, or equal to you have used previously whatever it is. Right now it will be odd with that, and definitely this component will indeed be enabled. Enabling means it is made low, don't think it is made 1. So this is to ensure that you are sending 0. It clears this bit, it clears the bit 1. Okay, and this sets the bit 1. So don't get confused why it is 1. It should be 1. It should be 1, and clear is 1 here. You are clearing the flag. Okay, and next what happens now, just observe one scenario. Three scenarios we have taken. We had data 11000000. So this is for the first iteration. Upon doing performing bitwise AND, you're going to get the value 1000. This is your answer. Okay, now again what we do is we perform 100. This is for the second iteration, 1000. After shifting again 1000, so you'll get again 1000. This is your output at the second iteration. So the output in this case is 1 you get, and that 1 is sent to the shift register. Again you have 1, that again is shift. So which means first first D flip flop over here, this flip flop which had 1 goes here, and the next data is in now here. So you have 1 and the remaining bits are all zeros. Okay, and finally repeat this process. So upon repeating this process, the result what you're going to get, I'll just address. If you just move according to this manner, so upon 8 clock pulse applying, so now the clock pulse is not applied. Upon applying 8 clock pulses, you are going to receive the data. C0 was the data here, so it was at the bit 0 position. Now it goes to this position, so you have 1 1 0 0 0 0 0 0. So that's how the shift register will have this information, that is on the lower side of the shift register. Now what you have to do is this whole 8 bits has to be moved on to the this shift registers, or this D flip flops, upper end of the D flip flops. To transfer this or to latch this information onto the upper D flip flops, you are supposed to trigger this line high. This latch clock should be enabled. So to enable this, again this should be pulled high. So when you pull this high, then this whole 8-bit information would be latched onto this line Q0 to Q7. Now Q0 to Q7, how it is connected? Q0 to Q7 are connected in this manner. So this A is connected to Q0, B is connected to Q1, and finally DP is connected to Q7. So now when the information what you have now is here you have 100. So just assume, what is this? This is 1100. What is this? This is connected to DP. So you have DP1 and you have G1, and the remaining bits are all 0. So this information is sent. So definitely on the LCD or on the 7 segment module, you'll be getting now 0 information. Okay, so that is achieved only when you apply a latch pulse. So what for latch it is P2 P22 pin. So P22 pin has to be set first. So for transferring the data onto the 7 segment module, first P22 pin should be made high and it is made low. So small amount of delay if you provide, that's fair enough. So this is for providing the latch or giving the latch. So in this case, the 8 bits will be transferred onto the 7 segment module. So this is how the structure looks like. This is what happens when you provide this function. So now what happens, one 7 segment module, the first 7 segment module will glow. Then again this will go back and x will become 1, and now again the display method is called. Now you don't have any difference here, but in this case what happens is the information is already available. So you can think as if in this shift register, you have 110000. Okay, this is your first shift register. So all this information should be moved to the second shift register. How it is possible? Again apply the clock pulse. So this bit will be moved from this place to another place, and data what you have now again, which is c0 gets occupied here, which means again c0 which was present here goes to the next shift register. So in the second shift register you can display the message now 1. So that can be enabled, others need not be enabled. So only in the second 7 segment module you'll be getting the result. Okay, and you continue the process 6 times, which means 0 which was displayed in the first 7 segment will be displayed on the second 7 segment, and it continues doing so till it reaches the sixth 7 segment module. After that what we need is after that this display 6 digit when this terminates, which means you get 0 displayed in all the 7 segment module. After that we expect 1 to be displayed. So what happens now, after this count is incremented, so count becomes 1. Now you compare whether the count is greater than 15. Definitely it is not, count becomes 1 now, and in that case this condition is not executed. So provide a small delay, wait, hold the information for a while, make yeah hold the information for a while, then go back to while program, then again now use display 6 digit. Now when display 6 digit is called, now again it goes here, this program continues 6 times. Now you have display of disp of, now what is the value of disp? This was 1 because count value is 1 now. So now disp of 1 value is different, it is f9, which is the code for 1, and in this manner the program continues. Well, this is the program. Hope this you are comfortable with this. So one more program, we will try to simulate this program using cortex in the next session. Thanks for watching the video.